Please go ahead.
Okay. So, hi everyone, I'm Aleksandra Faust, and I want to share today some of our latest work on learning to learn for reinforcement learning. And there are three ideas that kind of are open out there. So, reinforcement learning is all the rage nowadays, and if you're not very familiar with it, it basically entails an agent interacting with the world, observing what the world looks like and receiving some intermediate rewards, and then learning long-term behaviors or cumulative discounted reward from these partial observations and partial rewards. And I swear, used to say this, like, okay, this is super easy because you now just kind of have these rewards and you let it learn and you don't need to solve math and life is good and so on. Except that once the reality sets in, how we're training these things, like, okay, first question is, how do we select a reward? Not easy. Second question is, what neural network architecture should be there? Third question is, how to select RL algorithm, which one should I use, and so on. And finally, like, what environment should I put the agent with, how I should initiate. So there is tons of design decisions that we end up having to make. And this is very human in the loop process where an engineer sits there and says, okay, let's try this. Let's see what happens. Okay, let's try this, and so on. It's a trial and error. So if you kind of switch back and says, hey, this is actually a decision-making process that the human engineer is doing to get to these agents to work, right? Which is kind of the definition of what we're trying to do here in the first place. So if we're having human making all the decisions, that means that we can have an agent, train agent, doing and making all these decisions. So this is the idea that actually training RL is a decision-making problem and can be learned. So we'll go over three different examples here: learning the rewards, learning URL algorithms, and learning environments, or kind of figuring out what environments should be used. So on the first setting for the learning rewards, let's assume that we're in a setting of mobile robot navigation, and we want to solve a task of agent going from A to B in dynamic obstacles and so on. So observations are the goal, and basically sensor observations, and it needs to reach the goal, avoiding any obstacles that might come along the way. So in this case, the observations are noisy LiDAR observations that the agent sees. The actions are speed, angular, and linear velocity. Environment is just a very simple static environment in simulation. But then what the reward should be. We can say, hey, yeah, the agent should be rewarded when he reaches the goal, but that's sparse and it kind of leads to intractable training. So we do have a good intuition around what the reward or more dense reward would look like: the distance to the goal, the distance to the nearest obstacle, the orientation, the speed, and so on. But how these features fit in together, we don't know. So we can pose here a reward as a parameterized function of these kind of features that we know intuitively. Second question is also which architecture to choose. And in this case, we're just doing a simple how many layers and how wide they are. So how do we learn then these are hyperparameters really to the problem, these two weights. And just to give you an example, this is a train agent that's using different reward, and see how robot is kind of swirling around. That is suboptimal reward. So how to approach this? Basically, we have this parameterized reward. We initiate a population of agents, each one of them having different parameterization of the reward. Then we train them with RL, and we're evaluating how well they perform on the tasks. And we're evaluating what is basically expected success rate for reaching the goal. Then this goes into the mutator agent that observes basically what is, given the weights of the agents and given the outcomes, what is the next weights that should be tried, and basically spans off the next agent for the rewards. From there, basically we can select the best policy and the best reward that comes in. And there comes the second loop then, that we know our reward weights, basically learns the best reward that completes that task. The second one is now, let's do this with the neural network architecture. So we can vary, again, the number of layers and the widths and so on within that fixed reward. So let's try to fit the neural network architecture to the reward. And again, randomly initiates them. It evaluates them against the reward, and then selects the best architecture, proposes next architecture, evaluates it, and so on. And in this case, we are running 100 in parallel, about 1,000 agents at a time. And between these two things, we start seeing good improvements in the policy. The training algorithm in this case is in simulation. We train with the noisy sensors and randomize initial and goal conditions, and these two are giving the robustness of for the policies. And then to reach the goal, we learn with these parameterized rewards and neural network architectures with this population-based training and use the off-shelf algorithm. That RL policy directly transfers on a real system. And on the left, simulation, no moving obstacles. On the right, real system with the moving obstacles and so on. And the reason is because it makes a single decision at a time. So the moving obstacles move like, okay, who cares? And since it's a LiDAR, it's a depth sensor, so it doesn't care about the semantics of the object. And it's also the same method working across different robot morphologies. We try on fetch, on freight, or car racer, and other systems with academic constraints, which is exciting. So the next question was, okay, how generalizable this is? Is this just something that works for robot navigation, or does it work kind of across the tasks? So back we go to the standard RL benchmarks. Basically use 4 benchmarks and 3 different algorithms, soft actor-free PPO and DDPG. And we basically try to see whether in Mujako task, the standard reward consists of 3 or 4 different parameters, and we vary these parameters and we optimize against that parameter. And the conclusion, so the baselines here, the green is the standard baselines, the blue is we're tuning the hyperparameters, and the orange one is we're learning the rewards. And across the tasks, the more complex the task is, the more gain it is in getting the rewards, which basically says we as humans are bad at picking good rewards. Let the system do it. The second question, across all these tasks, we have these complex rewards in Mujako environments, but really the goal here is simple. For humanoid and this guy here with the two legs, an ant is move as fast as you can. For humanoid stand-up, it's get as high as you can. That's a very simple objective that we can encode very easily and so on. So the question is, does it even make sense to kind of create this complex reward that we want to optimize and so on? So in this experiment, we trained with the simple reward, but evaluated against the complex. And basically this delta here is the gap. So the moral of the story is here is like, again, for more complex tasks, just go simple. There is no really need to go and engineer the reward as the objective. And then the third question here that we asked was, okay, if I have this is a computationally expensive method. So if I have a fixed training budget, should I do hyperparameter tuning or should I learn the rewards instead? And blue line here is hyperparameter optimization. The orange line is the learning the rewards. And the conclusion is that we're more likely, if we're starting with the reasonable hyperparameters, we're more likely to get better results sooner learning the reward than tuning more hyperparameters. And this is exciting. So that was one example. The second example is learning loss function and learning RL algorithms. The idea here is that recently new RL algorithms are popping out like mushrooms. It seems like every 3-6 months we have a new RL algorithm. It's basically just tweaking the loss function. So fundamental question is, can we learn RL algorithm that performs well on unseen tasks? And the insight is that really loss function is a computational graph. And as a computational graph, we can involve it and change it and mutate it and evaluate it on target unseen environments and see what we come up with. So that's what we do here. This is in the DQN setting, so discrete actions. We train our training environments. First, we have a hurdle environment that the proposed loss function. So again, we initiate population of the loss functions as graphs. We train them all first on a hurdle environment. If it can't pass the hurdle environment, there's no point training it further. Then we have several other simpler environments where it's training, and it's being evaluated in these same environments. Then it goes to the mutator that selects and proposes the next graph from and spawns the new agent, and the process goes on. And once we select the algorithm, we use test environments that are not seen before, and they're different than seen before. So there are mazes and there are Atari, which we haven't used at all in training. And we come up with the DQN regularized algorithm, which is called the LearnRL. It is actually a version of the entropy regularization and similar to CQL now. It penalizes the Q values on the data set to prevent overfitting, which is very interesting. That's what it came up with. And how well does it perform? So here on this graph, purple is the learned algorithm, and it's compared versus DQN, DDQN, CQL, and so on. And you can see in the mazes, this is task it hasn't seen before, how much better it performs. It also generalizes to Atari games. The numbers here are taken from the reported numbers in the papers, so we did not rerun these numbers, and DQN runs this. And it's interesting here is that we trained it on non-image based environments, and it was not tuned at all for the Atari games. So that's exciting. And third takeaway is that across the seeds, we keep coming back to this algorithm or within a constant of this algorithm. And that's fascinating. The second part is that this is the first time that we have a database, and we released it, it's out there on a GitHub available, database of 1,000 different RL loss functions and algorithms and how well they perform. And what's interesting is that within these algorithms, most of them are not doing well. And then there are certain kind of local minima or maxima where they are performing well. So the question is there a huge secret that equivalency class of the algorithms that we don't understand, or the environments are not enough here? And I think that would be very interesting to dig deeper. Nice thing is these are graphs, so they are basically math formulas, and you can use the same tool set to analyze them and so on. And then the last topic that I want to mention briefly here is about the environments and how to use the environments. And for this purpose, I'm going to step away from robotics and talk about autonomous web navigation for a moment. So imagine yourself buying something, say on the Walmart website, or changing a Twitter password, or ordering food, or on DoorDash or whatnot. We can do this without any additional training. We know where we're in a task. You enter your name, you enter your address, you enter this and that, and you're done, right? This is actually more of a manipulation task. Because you're manipulating environment, you enter the name, something changes. Then you move on from first page, hit that next button, you're on the second page, and so on. And because we as humans can do zero-shot transfer or kind of don't need additional training to go between these tasks, can we have a single agent that solves any task in this class of related tasks, with the big question being, what is here related task? Why is a reasonable expectation to be able to do this? And why can we expect the generalization? So that's kind of the setup. So in the area of learning web navigation, basically we have something like a commercial flight booking website. It has something like a 30,000 DOM elements, or like the little things in the HTML that are there. And training on these is really not feasible. I mean, it's denial of service attacks. It's expensive. Buying million tickets to train your agent, not gonna fly. And then on the other hand, the existing benchmark only has 100 DOM elements per page. This is what it looks like. And the current state of the art solves single environment with millions of interactions with the website, right? So there is a huge gap between what is really reality here and what is available in the research community. So can we have autonomous navigation and manipulation for this compositional task? And we call them compositional tasks because they're consisting of the small pieces: enter first name, enter last name, enter address, drop down, right? And so on in these unseen real world environments. So the first question is, how do we understand what is a related task and what is the structure of the tasks? So we go to Petri nets, and I'll just, again, like a older version. If you're not familiar with the Petri nets, they're basically graphs. They have two types of nodes: places and triggers. Places are circles and triggers are rectangles. And then there is a little token there that basically defines the state. And token is at the place, and at the trigger happens in the rectangle, something happens to the system externally, and then token moves on to the next one. So basically, Petri nets define the structure of the tasks. It defines states, actions that the external agent kind of goes in to move these tokens, and the transitions. And there are well-established formalism that model asynchronous processes, synchronization points, they can even count, and so on. So in this space, basically, if we kind of look through the Petri net lens, a single agent, we want a single agent that solves any task in this class of related tasks. Basically, the primitives here are this first name, go from a state, enter first name, and then you enter the next one, address, and so on. We want to define a family of Petri nets, which kind of correlates to the family of POM MDPs. And we want to have a single policy that maximizes expected return over family of POM MDPs, which are induced with this family of Petri nets. And then that way we can kind of define the structure. So how do we go about that? We define learnable compositional tasks with this family of directed acyclic hyperpetri nets with colors that are induced with a given set of primitives. This given set of primitives, the first name, last name, drop down, whatnot. And basically they're consisting of pages with series of gates. This would be your rooms, right? Or the pages, and things that kind of need to happen on every single page. And then learnable, now we have the structure, we understand how to build this task and what is the space of the generalizable tasks. From there, we can start building these pages from the primitives. So given a set of primitives objects, we can create a set of pages, and then we can kind of connect these based on the Petri net allowed transitions. And that sets us then to be able to generate new websites that have not been seen before with the kind of arbitrary complexity. So then the question becomes, how do we train this? If we go and train this with just a small environments or kind of very complex, we're not going to get anywhere because the space is too big and it's not tractable. So instead, we do the two-agent training. We have an agent, a teacher agent, that proposes and basically generates a new website that the RL agent is going to train on. And then the designer, teacher, is going to observe how well the students are doing and adjust the difficulty, either make it easier or harder based on how well the students are performing. So it's a multi-agent setting. One Here, designer proposes environment and creates a generative website, synthetic website. And the second one is then training. So once it trains, the designer observes, we're training it on population of agents. The designer observes the regret and the agent performance and has two knobs to tune. One is what is overall difficulty, we call this budget. So how many elements across, you can create maximum to 10 pages. And on each page, I think 15 elements you can put. So budget defines, okay, across this whole space 10 by 15, how many elements I'm gonna use. And that is driven directly by the agent's performance. And then regret is basically in the population of agents, it tells me what is the difference between their performances, and it selects the particular elements in order to kind of create the more interesting tasks that these guys can, some are better, some are worse, and so on. So it's a dual loss function here. And kind of keep training that, and then we evaluate them in never before seen websites. And here is an example of one. This goes through 3 pages. So how well does this work? Environments become more complex with time. So early in staging, they only have few elements. Later on, they have many elements. 2, they generalize to unseen environments, and the difficulty and performance keep growing. The blue line is our method. The baselines are manually designed curriculum and so on. And then third, the distribution of the primitives shifts more towards relevant tasks later on in a training. And so some of these things are like, we have distractor elements and so on, and they disappear. So does it work in reality? We actually test them on 3,500 primitives that were scraped off the web, which induces the task space of 10 to the power 30, and mostly login task for login to a Twitter or something like that. And the performance on the login task is about 50–60%, which is actually what we get on the benchmark as well. When we actually apply it on the target websites where the primitives came in for, we're getting success rates in 90s, which is very exciting. So next question is, how do we improve the agents with the population-based, and what are different task topologies? But just kind of briefly to summarize, so we looked at 3 examples: how to select reward, and we saw there that evolutionary methods produce rewards that fit the environment, and the more complex the task is, the better, the more benefit it is. When it gets to learning RL algorithms, again, reinforcement learning algorithms show promise of learning new algorithms that fit in the set of the tasks. And then when it gets to the environments, we saw something different. We saw that learning curriculum and having an agent that proposes the new environments improves generalization. What's interesting about this is that first 2 methods, evolutionary, RL algorithm, and rewards, is more of the nature thing. What is the structure of the agent that fits the task? In the second side, compared to the prior work, we did not change the agent. The agent that we're training has the same neural network architecture, same reward, everything else. The only thing we change is what are the experiences that that agent is receiving? What are the environments? This is nurture. and we show that we gain huge improvements in generalization. So here's the fundamental question that I want you to leave you with, is what is the fundamental role of nature versus nurture in reinforcement learning? And I don't have an answer to that. I'd like to have a discussion around that, but something to think about. And with that, I'd like to thank my collaborators, and I want to thank you and open for questions.